Hello and welcome to Oak Ridge National Lab's Invention to Innovation webinar series. Today's presentation is on the Hyperion cybersecurity technology that'll be presented by Dr. Stacy Prowell. My name is David Sims and I'm a commercialization manager here at the lab. If you have any interest in licensing this or other technologies from the lab, please feel free to call me at 865-241-3808, or you can find my full contact information on the web at ornl.gov and follow the Our People link near the top of the web page. Before getting into Stacy's presentation, I'm going to take a couple of minutes to give you an overview of cybersecurity technologies and capabilities here at the lab. We have over 30 researchers in the Cyberspace Sciences and Information Intelligence Research Group who conduct research in cyber warfare, situational understanding, visual analytics, and information dominance. This research is done in order to defend the nation's critical infrastructures against cyber attacks, to understand threats in order to provide real-time, actionable intelligence, to secure supply chains and continue operational capabilities, and to defeat both known and future adversaries. The group is divided into two research teams, the Cyber Warfare Research Team and the Situation Awareness and Visual Analytics Team. Our guest presenter today is the leader of the Cyber Warfare Research Team, which currently consists of 13 people, 6 of whom hold doctorate degrees. The team studies methods of both attack and defense in cyberspace, and also manages the lab's Center for Trustworthy Embedded Systems, which operates a cutting-edge laboratory conducting research on the security of vehicles, medical devices, as well as the rest of the Internet of Things. To support this research, the team also operates and maintains its own private test networks, computational clusters, and storage units. The current research efforts include learning-enhanced moving target defense, physics-based intrusion detection systems, improvements in internet routing for enhanced resilience, and static analysis of compiled software, an example of which will be presented in today's webinar. Dr. Prowell is the Chief Cyber Research Scientist here at Oak Ridge National Lab, and his work focuses on applying high-performance computing and computationally intensive methods to understand automated reverse engineering, semantic analysis, system composition, and software forensics. In addition to being leader of the Cyber Warfare Research Team, Stacy also serves as the program manager for the lab's Cybersecurity for Energy Delivery programs, and holds a joint appointment in the Electrical Engineering and Computer Science Department at the University of Tennessee. Stacy has managed commercial software development projects and has consulted on the design, development, and testing of a wide range of applications. He also holds a PhD in computer science from the University of Tennessee. More information about our technologies available for licensing can be found on the web at ornl.gov by following the partnerships link, which is about midway down the web page. And in the next day or so, we'll have this webinar posted on YouTube, as well as a link to it posted on our partnerships website. So now I'm going to turn the microphone over to Stacy, who will provide a 15 to 20-minute overview of Hyperion, and afterwards he'll be available for questions. If you want to ask questions, remember to unmute your microphone, or you can email me questions at simsdl@ornl.gov. That's simsdl@ornl.gov. Okay, Stacy.
Great, thank you, David. And do feel free to interrupt me as I'm going through this and ask questions if you'd like. So I'm going to tell you a little bit about Hyperion, and I'll try to get my my 2-hour presentation down to, what did you say, David? You said what, 1 hour?
15 to 20
okay.
minutes.
Well, maybe. Let's see if this will work. Let me see if I can change slides with this. And it looks like I can't. Can you bump me to the next slide, please? Perhaps slide changing is another technology where we need to work on. All right, great. We've conquered the slide advance. That's a wonderful thing good technology to have under our belt. So really, Hyperion is trying to get at this problem that software tends to be delivered to you as a black box. It comes to you in this nice compiled form, ready to execute, and that's all well and good, but it contains programmed but unknown behavior. It may contain some ill-conceived behavior, poorly implemented protocols, weakly implemented crypto, weak random number generators, things like that. And it may contain correct behavior that is correct to its specification, but still insecure. And we need a way to discover all of this before adversaries do. You have someone who will find all this for you. It's your adversary, but we would like to know about it, preferably before they do, because then we can take steps to deal with it. Wow, there we go. So what we need is rigorous assessment of the true functionality of programs. We need to be able to take a piece of compiled software and say what it does. It's a hard problem, but it's made harder by a number of factors. Next. One of them is compilers. Compilers will come along and add value. They will, thank you. There we go. They can strip out secure behavior, and that's pretty well documented, and they can introduce compiler bugs. They add their own little features to it. So you have to work with compiled software in order to get things done. And you have to consider all the behavior. One of the things that will lead folks astray is the use of heuristics early on. It seems reasonable to conclude that incrementing a register is the same as adding one to it, but on the Pentium, they're not quite the same. So the little highlighted line there shows you that one will modify a flag called the carry flag, the other will not. And if you think that's not a big deal, that is in fact something that you see in malware. People can take advantage of this to determine whether or not they are being sandboxed or they're being emulated or debugged, because emulators will tend to get this wrong. The intuition of people reading the code, they'll tend to get this wrong as well. If you see an increment followed by a check on the carry flag, you're going to make an assumption, and that assumption is probably going to be wrong. So let me tell you a little bit about our solution to this problem, which is Hyperion. It's a system for doing static analysis, meaning we don't execute the software. We do some small amount of symbolic execution when necessary, but for the most part, it's swallowing the ocean kind of static analysis. We do it on compiled software. We can apply this to reverse engineer software to discover behavior. We've done it to compute similarity as well. The technology is fairly mature. It's been proven to work, and we've delivered it to a number of organizations. So if you're familiar with the technology readiness levels, this has been rated at TRL 8. And basically what it does is shown in that little figure at the bottom. You give it the bytes of the compiled program. You can give it a specification for a piece of behavior you're looking for, and those we'll talk more about. They tend to be fairly easy to write and maintain, and it will tell you whether or not it's present, and in fact tell you something about it if it finds it. So Hyperion began life back in 2004 at CERT up in Pittsburgh. We developed the initial version of it and applied it to polymorphic and virtualized code. There are some articles in the CERT research reports about it. And then in 2009, the project and the entire team, in fact, moved to Oak Ridge, and we changed names because it's important to deal with branding. We changed the name from FX to Hyperion, and there have been many different applications of it here. One of the things that I would say was the primary contribution to the technology after it moved was turning it into a product, turning it into something that was reliable, where you could deliver it. It had well documented, there's training for it, etc. All that was built out at Oak Ridge so that we could have a nice stable base on which to continue research. So here are the basics of how Hyperion works. We take compiled software, we perform disassembly, we handle anti-disassembly, which we'll talk a little bit about. We then do structured discovery, so we turn the disassembled program into a structured program. We do external call discovery, so if your program has no import table or the calls are obfuscated in various ways, we use information we discovered earlier in the process to reconstruct that and discover what the external calls actually are and what their arguments are. And then we do behavior discovery, which is where we actually use these patterns of behavior to recognize and document what it does. Right now, we have two platforms Hyperion can target. It targets 32-bit Intel, and it targets the TI MSP 430 embedded processor, just because those are the platforms that customers have asked us to deal with. So we do deal with anti-disassembly, and if you're not familiar with it, there's a little example down on the slide here. If you look at the example on, let's pick the one on the bottom right, the first 4 bytes are a move instruction. Those are followed by an XOR instruction that exclusive ORs the register with itself. The result of doing that is always 0. So that jump 0 takes you back. So you count backwards, E, D, C, B, A, 9, and that takes you back to that jump 5 instruction, which you see was part of the original move instruction, but now it's being reinterpreted. You jump forward 5, and now you're into the real code. A straight line disassembly, so if you just point the disassembler at this, you'll see the move, the XOR, the jump -7, but then you'll see a call instruction after that, and you'll be off and you'll not see the real code. So we have to deal with crazy disassembly, anti-disassembly techniques, funny things like that. The way that Hyperion deals with this is it does basically threaded disassembly. It allows a single address to appear multiple times in the final program. And the way we do that is sort of outlined on this slide here. We identify the entry point, we find main, we begin adding addresses to the stack and exploring the program. And that's almost true. And the reason it's almost true is because we have to do a little bit of everything to make any of this work. So it's a very iterative process. For example, we find main using a variety of methods, one of which is we look at the complexity of the structured islands we've discovered. And we typically find that main is the most complex of the structured islands encountered after the entry, and that works very well for us. So there are a number of ways that we can go about doing this, and they all require that you do quite a bit of work. But the end result is a static disassembly, even when you have the reinterpretation of some addresses. We then do structuring. We turn things into sequences, if-then else's, while loops, and we do extraction of it. So for sequences, it's function composition. For if-then else's, it's a very simple function composition. For loops, it's a little harder. There are a number of techniques we can use. We can do loop slicing. There's some work that we've done on using relations. We find that loop unrolling, which I didn't, for some reason, have on the slide, we find that loop unrolling works quite well. We can often unroll the loop and discover what it's doing pretty readily. If that doesn't work, we can fall back on slicing and other techniques. But what we ultimately get out of this is what we call a program function. So given a barrage of instructions, we boil that down to its net effect. So what you see there, the result is, in this case, a list of the flags that are modified and what the new value is in terms of the prior value. So what you don't see in that little list there is any registers, and that's because the net effect of this sequence is to leave all the registers unchanged. This is a no-op, and I can't recall what piece of malware we got this from, but it came out of a piece of malware. It was sprinkled liberally through it, and the end result was to make the program very, very long and difficult to disassemble. Hyperion discovers these are no-ops, takes them out right away. That takes us to call traces. We have the computed behavior, we've reconstructed the external function calls, and now what we need to do is transform the result into a call trace. And we do this, I should point out, across function boundaries. So we discover what we think are functions, we generate call traces, but we also do this across function boundaries so we can recognize behavior that may start in one function and proceed across many. We use a term rewriter to do this transformation. And the nice thing about call traces is that this is something that software engineers think they understand. When they see a Windows call, they believe they know what that means, and so they can reason about it. And in fact, that's how we go about defining behavior specification units. Here's an example of a call trace taken from Hyperion output for a piece of malware, and we see a number of things happening here: open process token, duplicate token, and impersonate logged on user. This is an interesting little sequence, and when we looked up this little sequence of stuff, we found some code on Google Code. This is code used to bypass the device driver signing on Windows. And if we take those two pieces of code and we overlay them, we see they line up very nicely. And that hints at a process. It hints at going back taking this, turning it into a general pattern. So replacing some of the specific stuff in there with don't cares or with the pieces that link it together. So you see the H token in green has to be the same H token passed to duplicate. You see that in the next one, the H new token has to be the same H new token passed along to impersonate logged on user. So we replace those with variables so they line up, and then we can identify that pattern wherever it occurs. And in fact, that's what we do. We call those behavior specification units. There's a high-level language that makes them very easy to write. If you can write programs for Windows, you can very easily write these. If you're not quite up to writing programs for Windows, you can probably still write these because it's a very simple language geared toward writing these patterns. What happens, of course, is these patterns get compiled into nasty, nasty math that you never want to see, and that's okay. That happens behind the scenes. So here's a snippet of one of our BSUs. This one is one we use to recognize anti-sandboxing techniques. So if you match this, you're probably malware. We took a lot of these from Paranoid Fish, which is cited at the bottom there. Paranoid Fish is an example of various anti-sandboxing, anti-debugging techniques. And you can see we reference other BSUs. So there's a BSU somewhere called check for small disk size. There's one called check for mouse movement, etc. And then the rules at the bottom tell us if you match any of those, under any conditions, we want to apply this anti-sandbox tag to that piece of code. So we can look for any of this stuff. If Hyperion finds any of this in the call traces, it labels it as anti-sandboxing, and then you can go and look and see what's actually taking place there. And it's easily expanded as we write. In fact, this is a snippet of the larger one. As we discover new kinds of anti-sandboxing, we just add another BSU and another rule to it and easily expand this. Here's our keylogger detector in full. So somewhere there's a BSU called get key press. It's what you might imagine. It's all the different ways on Windows that you might collect a key press, followed by file write complete. And that's all the different ways in which you would write to a file. We have a couple of things going on here. One is key press has to be the same in both. So we know that the key press that was read is the one that's eventually written. File is part of the file write complete BSU, but we don't care about it here, so we just say we don't care. And the rule says that I have to have B1 followed at some point by B2. Things can happen between the two. Things can happen, and any BSU that matches either one of those is fine. And these can in fact happen in different functions in different parts of the code. The point being, if I find a new way to read a key press on Windows, I just add that to the get key press BSU, and nothing else has to change. If I find any way to write it, I add that to the file write. Nothing else has to change. If I get interested in people writing key presses to the network, well, then I add a new line that says network write complete, and be sure that the key press is what's referenced there. And I can add a second rule, which then says B1 followed by presumably B3. And either one of those would catch this. The point is, BSUs are very simple, conceptually simple. They're easy to write. They're pretty easy to read. They have a few special symbols in it, but not that much. Dollar signs, denote variables, underscores, don't care. You can learn that very easily. They're very easily extended, and they're very robust. So here's a slide example of it. Here's some bytes from an actual piece of malware. This was some malware that was used to attack Oak Ridge National Laboratory back in 2011 that we captured. We can disassemble it. There's part of the disassembly. And for those of you who love reading disassembly, this is great. You can structure it. So you turn this into, you do call recognition, and then you do structuring. And so we see if then else's popping up. We would see while loops, etc. And that could be helpful. But let's turn it into a call sequence, because that will surely clear it all up once we see the call chain. So there it is, and I'm sure that clears it all up. So you can see what's going on: open process, virtual allocation, write process, etc. A lot of stuff in here. But the Hyperion system does the bookkeeping, boils all this down to the one thing you really care about, which is that piece of code is doing process injection. So we get a BSU match. It matches across all the bytes of it, and it says, this piece of code is doing process injection. The first argument, I believe, specifies the process into which you're going to inject. The second one, it specifies the code you're going to inject, and the third is a delay, so that you can hopefully avoid detection. And we get that without actually executing any of it. We match it. We can see which parts of it match that and what's going on. So again, this is a summary of where we are. TRL 8, we've delivered this to a number of organizations. It seems to be working well. We're collaborating with folks at the Applied Physics Lab, at Lawrence Livermore, at Pacific Northwest National Laboratory, and at Sandia National Laboratory. The term rewriter that is used in the system is open source. So if you go up to GitHub, you can go and grab that. We have about 237 behavior specification units, which allow us to match a very large corpus of malware. We have our own malware corpus here. We work with some external organizations that have their own. And so we're routinely looking at our coverage of this. We've got right now 237 BSUs, and we're doing really good matching. And that is about 3,500 lines of BSU, non-comment source statements. So you can see doesn't take a whole lot of writing to get a BSU that's going to be very robust and match a lot of bad behavior. Presently, our top-level malicious BSU finds a whole bunch of good stuff. It finds process injection, service enumeration, key logging, anti-VM, anti-debugging, uploading and downloading behavior, and a whole raft of others that we've introduced to catch all the malware. So that's the status of the system, and I'd be happy to answer any questions you have about it.
This is Dan Strelis at Rapiscan Labs. I had a question about, maybe you could go a little more detail into the type of testing that was done in the national labs.
So the Hyperion system was selected by the Department of Homeland Security for its transition to practice program. And as part of that, we delivered the source code, the documentation, et cetera, to Sandia National Lab. And they did a pretty thorough red teaming of it. They red teamed all the technologies that were selected for this program and created a comprehensive report of it. And I believe that report is available for folks. Yes, David is nodding his head at me, so that report's available if you'd like to see that. They deployed Hyperion on their farm malware repository, and to the best of my knowledge, last time I talked to Steve Hurd, they were still using it there. So it's been vetted by them. It's been put through its paces at two other organizations as well, who both done that. I don't think those reports are publicly available, though. David's shaking his head at me, which means no. But it's been through some pretty significant testing. Like I said, we have our own malware catalog here that we routinely run it over, and at least one of our other partners has a pretty comprehensive malware repo, and they pretty routinely run it over that and to see what they can catch and discover.
All right, thanks.
Sure. What else can I tell you?
No, nothing else. Thank you. That was good.
Sure.
So there's one question that came up. Can you describe where this may be in use without going into details of who is actually using it?
So I guess I could mention mention that there's a commercial company, RNK Cyber Solutions, that has licensed this for commercial use, and they are and I think they're repackaging it to have nice GUIs, etc. Something we didn't care all that much about here. It's in use by a number of other government entities have requested it from us under the government use rights, and we've delivered it to them. And a couple of them are still in pretty close contact with us. We know that they're using it. I can tell you that they're using it to screen new software, and in one case, they're using it for its original purpose, which is to analyze malware. So they're using it pretty heavily. I don't think I can name any of them, unfortunately, but it's in use. I'd say there are 6, maybe 7 organizations where this has been delivered and is in use.
And as far as licensing goes, we have licensed it to one company, but we're licensing it on a non-exclusive basis. So we intend to license many more copies of this.
Yeah, and I think we've been approached by a second company about licensing. I think I forwarded that to you.
Mm-hmm.
Okay. The one thing I didn't do today was show you a live demo of the system. I'd be happy to do that. It's very text oriented, because it's intended to be run sort of behind the scenes to scan software. It's there is an interactive version of Hyperion called the eViewer, and if you'd like to see it, we can arrange a time to actually do a live demo of the system for you. But that's not within the scope of the time I had available today.
Okay, I don't believe there's any other questions. So thank you, Stacy Proel, for giving your time of this and going over this.
My pleasure.
Dan, do you have any other questions?
No, I don't. Thank you.
Okay, great. Thank you.